In this video, we will look at the Kruskal algorithm to compute the minimum cost spanning tree. The Kruskal algorithm uses greedy method to construct a minimum cost spanning tree. The idea behind the Kruskal algorithm is to add an edge to the spanning tree in the increasing order of their cost. The optimization criteria is to select an edge in the non-decreasing order or increasing order of the cost of the edges. The edge is included in the spanning tree if and only if that edge does not create a cycle. Let us consider an example to look at how the Kruskal algorithm works. Let us consider a graph with 7 vertices and its edges. The Kruskal algorithm starts by considering each vertex as its own tree in a forest. A forest in graphs is a collection of subgraphs. So we have a forest with all the vertices and no edges. Then Kruskal algorithm maintains a set of edges A which forms a spanning tree. Initially, the set of edges A in the spanning tree is empty or null. Then in each stage, the algorithm considers each edge in order of increasing cost. So in the graph, the edge with the minimum cost is 10 between vertex 1 and vertex 6, and this edge is not in set A. Now since the edge between vertex 1 and vertex 6 is not in set A, and adding this edge will not create a cycle in the spanning tree, therefore the edge between vertex 1 and vertex 6 is added to set A and is part of the spanning tree. Then in the next stage, the next edge with the minimum cost is 12 between vertex 3 and vertex 4, and this edge is not in set A. Now since this edge between vertex 3 and vertex 4 is not in set A, and adding this edge will not create a cycle in the spanning tree, therefore the edge between vertex 3 and vertex 4 is added to set A and is part of the spanning tree. Then in the next stage, the next edge with the minimum cost is 14 between vertex 2 and vertex 7, and this edge is not in set A. Now since the edge between vertex 2 and vertex 7 is not in set A, and adding this edge will not create a cycle in the spanning tree, therefore the edge between vertex 2 and vertex 7 is added to set A and is part of the spanning tree. Then in the next stage, the next edge with the minimum cost is 16 between vertex 2 and vertex 3, and this edge is not in set A. Now since the edge between vertex 2 and vertex 3 is not in set A, and adding this edge will not create a cycle in the spanning tree, therefore the edge between vertex 2 and vertex 3 is added to set A and is part of the spanning tree T. Then in the next stage, the next edge with the minimum cost is 18 between vertex 4 and vertex 7, and this edge is not in set A, but adding the edge between vertex 4 and vertex 7 will create a cycle in the spanning tree. Therefore, the edge between vertex 4 and vertex 7 is not included in set A and is discarded. Then in the next stage, the next edge with the minimum cost is 22 between vertex 4 and vertex 5, and this edge is not in set A. Now since this edge between vertex 4 and vertex 5 is not in set A, and adding this edge will not create a cycle in the spanning tree, therefore the edge between vertex 4 and vertex 5 is added to set A and is part of the spanning tree T. Then in the next stage, the next edge with the minimum cost is 24 between vertex 5 and vertex 7, and this edge is not in set A, but adding the edge between vertex 5 and vertex 7 will create a cycle in the spanning tree. Therefore, the edge between vertex 5 and vertex 7 is not included in set A and is discarded. Then in the next stage, the next edge with the minimum cost is 25 between vertex 5 and vertex 6, and this edge is not in set A. Now since the edge between vertex 5 and vertex 6 is not in set A, and adding this edge will not create a cycle in the spanning tree, therefore the edge between vertex 5 and vertex 6 is added to set A and is part of the spanning tree. Then in the next stage, The next edge with the minimum cost is 28 between vertex 1 and vertex 2, and this edge is not in set A. But adding the edge between vertex 1 and vertex 2 will create a cycle in the spanning tree. Therefore, the edge between vertex 1 and vertex 2 is not included in set A and is discarded. Now, all the edges of the graph are considered and there are no edges left in the graph to be examined. So, the Kruskals algorithm terminates and we have a minimum cost spanning tree. The cost of the spanning tree is sum of the cost of all the edges of the spanning tree. So, the cost of this spanning tree will be cost of the edge between vertex 1 and vertex 6, which is 10, plus the cost of the edge between vertex 6 and vertex 5, which is 25, plus the cost of the edge between vertex 5 and vertex 4, which is 22, plus the cost of the edge between vertex 4 and vertex 3, which is 12, plus the cost of the edge between vertex 3 and vertex 2, which is 16, plus the cost of the edge between vertex 2 and vertex 7, which is 14. So, the cost of this spanning tree is 99. So, this is how the Kruskals algorithm works. Now, having seen the working of Kruskals algorithm, let us look at the pseudocode of the Kruskals algorithm. This algorithm is called Kruskal and takes 4 parameters. The first parameter is E, which is the set of edges of the graph. The second parameter is the cost, which is the cost adjacency matrix. The third parameter is N, that is the number of vertices in the graph. And the fourth parameter is T, which is a two-dimensional array and will be storing the edges of the minimum spanning tree. Then within the algorithm, we will first construct a heap out of the edges cost using the heapify function of heaps. This is because we consider the edges in the order of increasing cost. Now, the Kruskals algorithm uses disjoint sets, since all the vertices are initially considered to be disjoint, which forms a forest and are assigned to different sets. Therefore, we need to have a parent array for the disjoint sets and initialize all the elements of the parent array to -1. To do this, we have a for loop from I 1 to n, where n is the number of vertices. And within this for loop, we will initialize all the elements of the parent array to -1 using the statement parent of I assigned -1. The disjoint sets and their operations are also used to check if the edge added creates a cycle. Then we will use a variable I, which will be initialized to 0, and this variable is used as an index for array T. Then we will use a variable minCost and initialize the minCost variable to 0. This minCost variable will be storing the cost of the minimum spanning tree. Now we need to select a minimum cost edge at each stage and include in the spanning tree if the edge does not form a cycle. Therefore, we will use a while loop with the condition I less than n-1. Here, we use n-1 because for a tree with n vertices, there will be n-1 edges in the spanning tree. And the other condition as heap not empty. This means there are edges in the heap. If these conditions are true, then within the while loop, we will delete a minimum cost edge from the heap. Let this edge be between vertex u and vertex v. And obviously, after removing the edge from the heap has to be adjusted using reheapify function of heaps. Then we need to check if considering the edge between vertex u and vertex v forms a cycle. So we will use the find operation of the disjoint sets to find which set vertex u belongs to using the statement j assigned find of u. And we will use the find operation of the disjoint sets to find which set vertex v belongs to using the statement k assigned find of v. The find operation of the disjoint sets returns the parent. So if j, which is the parent of vertex u, and k, which is the parent of vertex v, are equal, then it means vertex u and vertex v belongs to the same set, and including the edge between vertex u and vertex v will create a cycle and is discarded. But if j is not equal to k, that means the vertex u and vertex v do not belong to the same set, and including the edge between vertex u and vertex v will not create a cycle. So, if j is not equal to k, then variable I is incremented using the statement I assigned I plus 1. Then we add the edge between vertex u and vertex v to the spanning tree using the statement t of I, 1 assigned vertex u and t of I, 2 assigned vertex v. That is, vertex u is assigned to the ith row and first column of array T, which stores the vertices of the spanning tree, and vertex v is assigned to the ith row and second column of array T, which stores the vertices of the spanning tree. Then the min cost variable is updated with the cost of the edge between vertex u and vertex v using the statement min cost assign, min cost plus the cost of edge between vertex u and vertex v. Then, since the edge between vertex u and vertex v is added to the spanning tree, we need to join the trees of the forest represented by disjoint sets. So, the set containing vertex u and vertex v are combined using the statement with the function union passing j, which is the parent of vertex u, and passing k, which is the parent of vertex v. Now this while loop continues deleting each minimum cost edge from the heap and executes the statements within the while loop until the heap is empty or the condition I less than n minus 1 is false and the while loop terminates. Then finally we need to determine if the edges included in the spanning tree actually creates a connected tree. Therefore, we check if I is not equal to n minus 1. If this is true, that means the tree is not connected. Because if the edge is included in the spanning tree, then within the while loop we will increment the value of I within the if statement. And for n vertices, there should be n minus 1 edges for the spanning tree to be connected. Therefore, if I is not equal to n minus 1, then the tree is not connected and we display no spanning tree. Otherwise, we return the minimum cost of the spanning tree using the statement return min cost. So, the Kruskals algorithm will compute the minimum cost spanning tree and returns the minimum cost. The edges of the minimum spanning tree are stored in the array T, which is passed as a parameter. So, this is the Kruskals algorithm. Now, let us analyze the complexity of the Kruskals algorithm. The first statement constructs the heap of edge costs using heapify algorithm, which takes O of E log E times. Here, E is the number of edges in the graph. Then, the for loop which initializes the parent array for disjoint set operations executes for n times and takes O of n as the complexity, where n is the number of vertices. Then, the while loop executes for at most E times, where E is the number of edges. Then, the statement of deleting a minimum cost edge from the heap and reheapify will take O of log E time to execute. But since this statement is within the while loop, which itself takes O of E as the complexity, therefore this statement will be taking O of E log E times to execute. Then other statements within the while loop and outside the while loop are primitive statements. Therefore, the overall time complexity of the Kruskals algorithm is O of E log E. So, this is how the Kruskals algorithm works and its algorithm and the time complexity.